Today's topic, optimizing materials from the very basic theory to some details within Unreal Engine. Instead of some concrete examples, I would rather stick to some synthetic ones. Take a look. Tim Jones has something called Shader Playground. So the Shader Playground is a collection of typical popular shader compilers from HLSL or GLSL to assembly. So it doesn't serve a purpose in itself. It's for diving into the shaders, checking out what our code is converted to. So, as I said at the end of the previous stream, assembly language is easier than you think. Okay? This is the most basic shader. If you are used to using nodes in Unreal, you may find it scary, but it's not. In general, here in the PS input, we have vertex attributes. This one has only vertex color. And here is the main shader program, which returns the final color. In Unreal, you are probably used to the fact that we have multiple outputs like base color, roughness, normal. Here, it's more like an unlit shader with only emissive color on the output, because this is how actually shaders behave. But in Unreal, they are packed, they are wrapped, and then the output is written to gbuffer, like the base color, the roughness, and so on. All the attributes are written to full screen buffers, and then there is another shader invisible for you, the user, or the game developer, which is the lighting shader that's run after this. But these are all details of a very complicated pipeline, and actually we don't care. If you want to measure performance of a shader, we don't care how much it takes to render lighting, we don't care what's happening before and after, because we should only care about what we can influence, which is the actual content of the material. So it doesn't matter if we learn what's heavy and what's fast on the synthetic example, this knowledge will be equally, applicable to final materials. Jeffrey says, I missed your previous stream. Will I need some stuff from the previous stream to understand this one? No, don't worry. I only showed this at the end, kind of a bonus, and I will start totally from scratch. So yeah, you're good to go. So this thing, shader compiler. By default, it uses Microsoft's compiler, which outputs something like this. And this is a modern assembly of DirectX 12 probably, or late 11. And it's very, it's very efficient. I think it's based on Clang, if I'm correct. Very good assembly for the computer. Not so much for us, humans. As you can see, there's load input, store output, weird symbols that then they point to some other places in the code. It's all good if you're a machine, very efficient. But actually I prefer the old style assembly. So we can switch either to FXC, the previous compiler, or to my favorite Radeon GPU analyzer. Let's use this one. As you will be able to see, the assembly will be very different. Like this. This is all. And these are the actual commands for the GPU. So it doesn't matter yet what it is. I will explain everything, so don't worry. The most important thing is that we can switch from this assembly to ISA breakdown, which is almost the same. But in this breakdown, we have the cycles column. And the cycles are the actual cost in GPU cycles for this program, for this pixel. And if this says 4, it's always 4, no matter what. Of course, it may depend on the hardware. So here, ASIC is the actual graphics card that you're aiming for. Here it's not explained, but in general, the biggest number, GFX 1030, are the newest Radeons, the RDNA 2 ones. So currently newest as of 2021. GFX 900 is the previous generation, but still modern, still newer than PS4 and Xbox One architecture. And now, where to learn the keywords? There is a great article, how to read shader assembly, just like that. Okay. And the article by Costas begins like that. When I started graphics programming, this is a quote from an article, shading languages like HLSL and GLSL were not yet popular in game development, and shaders were developed straight in assembly. When HLSL was introduced, I remember us trying for fun to beat the compiler by producing shorter and more compact assembly code by hand. This is an interesting thing. Compilers, by default, optimize everything they can, and shaders are such a simple environment, such predictable environment with not too many instructions, to be honest, that compilers can do a really great job in optimizing. So first, before I explain what it is, let me output something different. Or maybe I will explain that if you have, let's name it, because this is what it is, vertex color, okay? And on the output, you have float 4, which is RGBA. Come on, compile. Yeah. Then you have move. So move is assigning something to a variable, to a target register. Interp is interpolating the vertex attributes to the pixels, because pixels cover, some triangles, and the vertex color is linearly interpolated smoothly between vertices. So this is what that is doing, interpolating the value from the vertex in the pixel. Then it's converting CVT from 16-bit to 32-bit, float F. If you see F in assembly, it's usually float. If you see I, it's integer. And then export and end program. This is it. So this is doing nothing else than just taking vertex color, interpolating it between vertices, putting it on the screen, the end. Okay, now let's try this. Input vertex color times 2. And if you wonder if this is useful in Unreal, yes, it totally is, and I hope you will see later why. Okay, the new breakdown. What has changed? Still interp, still convert, but in the middle there is new thing. There's mul, short of multiply. Multiply some 32-bit float numbers. And the multiplication is happening 4 times because this is float 4 components of the vector. Each of them is multiplied by a constant that you can see here, 2. And each of these multiplications will take 4 cycles, like so. So now, let's try what will happen if we... By the way, I may also reduce this from float 4 just to make the assembly shorter. Let's say that this is not a vertex color per vertex, it will be some mask per vertex, okay? And my output will also be float, just for simplicity. Float. This won't compile, of course, because vertex color is not here. Return input mask times 2. Let's go. Okay, cool. The assembly is shorter, more readable, I hope. So it's interpolating just this attribute, And what? And it's adding? Why? Ah, because it's times 2. So it's the same thing plus the same thing. So I think here you can already see some optimization this compiler is trying. Okay. Compiler, stop cheating. Because now I will use return sine of math. Alright. As you can see, sine is an actual instruction on the GPU. But the input has to be altered a little by this, multiplied by this number first. Then it's given to the sine instruction. So in total, sine takes 20 cycles on the GPU. Okay, let's open Unreal's material and I will show you what Unreal does with the sine. We have a test material. I will change it to unlit. And by the way, there is some overhead from having a material because, as I said, it has to do some instructions first, some instructions after, because Unreal has a complicated, detailed pipeline of rendering. It's not just straight to the screen, okay? So first we need to test what's the basic cost, so cost without anything. So I will do an emissive color. Can be a float, I think. 1. That's it. Oh, Piatnashkin says that this magic number in the compiler is 1 by 2 pi. 1 by 2 pi. This is it, yeah. So I think that the sine instruction, the GPU, it doesn't work with the typical period of 2 pi. So it has to scale the input to use that and give the correct result. Right, Piatnashkin? Probably this is like that. Okay, so back to Unreal. We have material that does nothing and outputs 1. Now let me show the stats. And Unreal says that the base path shader without lightmap takes 29 instructions. Okay? 29 instructions. Now the important thing is that if we test optimization, we always do that on live parameters, like this. My param. Otherwise, you risk that the compiler will flatten the math because constants, like for example, this plus this, and if this is a constant and this is a constant, 1 plus 2, then the compiler already knows when compiling the shader that this is always 3. This always equals to 3. So what will happen is it will just collapse that to a constant 3 in the background, okay? So no matter that you placed add here, if you add constants, it will just replace them with the result. I can prove that here. So if we return not sine of input mask, but if we return 1 plus 2 plus 3, and let's wait for it. Yeah. So as you can see, there are no calculations, just the export of this, which is probably 6 in hexadecimal. Okay, so the same will happen here. Currently it's 29 instructions, right? But if I add and then multiply, but everything by a constant, let's say 3 plus 1 times 2, and to the output, you'll be able to see that it's still 28 instructions. The compiled thing has still 28 instructions, because this doesn't matter. The return value is known compile time. Constant folding optimization, exactly. Constant folding. Oh, using the custom node in Unreal prevents constant folding and may use significantly more instructions than equivalent version done with built-in nodes. let's try. By the way, let's try how it counts that. Okay, so custom is a node where you write HLSL code. So code is here, and let's write, and it will be x plus 2 times 4, 31 instructions. So as you can see, using a dynamic parameter already adds more instructions. Now, if I will use that here instead, 29 instructions. So yeah, that's true. That using a custom node produced more instructions actually. It didn't fold the constant here. Okay. So anyway, back to this. We had my param and now my param. If I multiply that with another param, let's say, or no, if I multiply that by some constant, multiply, let's say, and add. Okay, multiply and add, multiply by 3 and add 1. Cool. And let's try that. 29 instructions. Now check this out. If I use a sine node that we already know is 5 times more expensive than multiplication, 29 instructions. So it's not that Unreal is so optimal, no. It's that this is actually fake. 29 instructions according to Unreal are produced by that code compared to this code. This can't be true. Sine is much more expensive as an operation. Now take a look, sine and then cosine. Cos. So it should add 40 GPU cycles. 29 instructions. So take a look here. If I have my input mask, let's say, okay, this is mask, and I will also have text score 0, for example, I don't know, UV, okay, and it will be mask times input UV X, okay, and now the breakdown. So you can see there is a multiplication here. 4 cycles, right? This is it. This doesn't matter. This doesn't matter. 4 cycles multiplication. Now, instead, I will do return sine of input mask times input UVX and breakdown. So there are 2 multiplications. First by the UVX here, 4 cycles, by the constant that Piatnashkin mentioned, this one by 2 pi, 4 cycles, and then sine 16 cycles. This is what changes. Instead of 1 multiplication 4 cycles, we have 24 cycles by adding this sine. Now, if I add cosine to this thing, you'll be able to see that we will have at least another 16 and probably even 20 cycles more. Okay, cool. So breakdown, there's mul 4, cosine 16, there are another mul here, 4 and 4, and sine 16. So this is at least 40 cycles more than just the multiplication. 40. And Unreal says that it added just 2 instructions, sine and cosine, 1 and 2. This is not true. So this instructions has a huge problem hidden in itself. It doesn't show you the GPU cycles. It shows you the basic, I don't know, HLSL instructions. But instructions differ a lot in the cost, one compared to the other. Multiplication is the cheapest one, 4 cycles. Sine and cosine are 20 cycles. Now, instead of this, sine, let's use tangents. Tan. So yeah, tangents is made out of sine and cosine and reciprocal. Reciprocal is 1 by x. Then multiplication. So 4 cycles, 16, 16, 16, then 4. Yeah, so this is a heavy instruction. Now, if I used tangents here and compile, 29 instructions. So yeah, basically Unreal's instruction count is, how to put it lightly, an approximation, but often it's total nonsense. Yeah, so if you are in doubt, try to convert your code to HLSL in Shader Playground. Yeah, one more thing. If you have something like, let's say, deter temporal AA, and this is the green node, the most basic one. This is a blue node, so it's a material function. While for many of you it may be obvious, remember guys that you have to look inside. Double click that. And you may be surprised what you find there. This material function deter temporal AA contains even more functions. And when thinking about the cost, you have to basically sum everything. Okay? So it has some constant add, another add, divides, custom, look inside, there's a modulo, cast to uint, addition of 2, another cast to uint, multiplication, modulo by 5. So there's a lot happening here in a simple single node. So be careful. Even simpler ones like, you know, chip contrast or chip something. Oh, rotate about word axis cheap. Very cheap, right? The name implies that. Looks like this. And each of these nodes are actually not so yeah, cheap, because there's cosine, sine, sine, cosine. 3 times. Okay? Of course it depends, because in Unreal, if you connect only one of the outputs, if you connect only this, then the rest won't count. Let me show that. So I have my param, which is the rotation amount, and the x-axis, okay? Let's apply. 37 instructions. Now, what would happen if I choose the max of 2? Max is a very cheap instruction, 4 cycles by the way. If I choose the max of these 2, it's immediately 33 instructions. It's not because of the max, it's because of the fact that unconnected pins don't count. They are cut away. So yeah, connecting things adds them to the calculation if they end up in the output. If they don't, like this, they immediately stop counting. See, I connect that, 38. I disconnect that, 28. So 28 in this example is our baseline. Now, about this optimization. Take a look. If I have a variable float, let's say result equals tangents of input mask, but then I don't output this, just return 2, then the compiler will optimize that away. You'll be able to see that in a moment. So breakdown is super short. It does nothing. It just exports 2. Move, so assignment to the register, and then exporting this register. Job done. So yeah, as you can see, compiler does a great job. Okay? Now take a look. If I, let's say, if I, let's say, do something in an unoptimal manner, let's come up with something stupid. Let's say we have float. Okay, float result equals tangents input mask as it was. Then result will be multiplied by a fractional of uv of input uvx. That's good. Let's return that. You will see the proper output. What's happening here? Tan is done through sine, cosine, reciprocal, which is 1 by x, 16, 16, and 16 cycles, so quite expensive operations. Then fract, which is frac modulo by 1, it's 4 cycles, multiplication, and that's it. Cool. Now, what if I did something stupid, and if I multiply the result in the end by, let's say, 0, like this. As you can see, the assembly became much shorter. It just exports 0. Okay, because it knows, the compiler knows that this will always end up as a 0. So in this how to read shader assembly, it's written that they tried to beat the compiler for fun by producing shorter and more compact assembly code. But the thing is that modern compilers in the current iteration are so good, it's really hard to beat them without doing a meaningful change in the algorithm itself. Okay? So if you can come up with some optimization that actually, you know, cuts some corners, that uses a different approach, then sure, it's worth trying. But if you're just thinking you're clever and you're trying to change the order of some operations or something, don't bother. Compiler is great at this. Every compiler actually at this point. So Sony, Xbox, and AMD. Don't try beating it in simple math, okay? So if you, let's say, multiply the result by 3 plus 2, you will see that the add would be cut out. So in the ISA breakdown, there's multiply by this, a constant of 5, but there is no add anywhere. This was just converted to 5 that I can prove by replacing that. The same number, actually, just 5. So compilers are, yeah, the commit, you are right, multiplying by 0 is the ultimate optimization. It results in the shortest assembly and the least memory usage. Okay? Just kidding. So this thing. Now, there is another concept in compilers about which we should talk now, is the changing the orders of the operations if it makes sense from the optimization perspective. It does so automatically when the changing the order doesn't alter the result. Let's say we do float, and this will be, let's say, apply tangents, and there will be a float value va. This is a function in HLSL, and it's similar to making a material function in Unreal. Okay. So this will return 10 of va, like this. Okay. Applies tangents to input mask. Result 2 will apply tangents to input mask again, and this again, the same thing. And the actual result will be result 0 plus result 1 plus the result 2. So we have a clear order of operations, right? Apply tangents again, apply it again, then 2 additions, right? not quite. Take a look. What's happening is that it just the tangents once, these 4 instructions, and then it multiplies the result by 3, constant 3. Okay? So it found out what we're trying to do. It thought for a while and came to a conclusion that we are stupid as humans. So it used its computer magic to convert this into basically 4, 16, 16, 16, and 3 times 4. When I disable that, and if I just do result 0, and then return result 0 times 3, it will be the same assembly, probably. Yep, as you can see, exactly the same assembly. So 16, 16, 16, 4, 4, 4, and multiplication by the constant 3. Exactly the same code that it produced automatically before out of this. Knowing that we humans have limitations, we are stupid, and it used its computer magic to find out the better way. So we didn't beat the compiler by doing this. It resulted in the same output. Now there's another thing when it comes to the order of things. There's a node that you may remember. Texture sample. You have some texture sample param, like this. Let's call it my text. My text. Param2D, no. Texture object parameter, my text. This is a texture file, basically. This one, for example. You put it into the texture, you apply, let's say, UVs multiplied by scale, or tiling in that regard. You put it into UVs and you output the emissive color from this one. Super cool. It says 31 instructions. No. The texture sample is one of the heaviest instructions in terms of cycles. Not the instruction itself, it's cheap, but the fact that it has to wait for the texture to come from the memory. The thing is that if you have GPU, let's say here you have your shader core, like so. Okay, you have your shader core. Near the shader core, there is the fastest memory. Inside it, there is inside the shader there is a one super fast cache, and slightly outwards should be L2, L3. So the slower memory. Slower, but still extremely fast. Faster than RAM. Okay? Faster than GDDR5. And somewhere there, because we have many of these cores working on many pixels at the same time, somewhere there you have actual, maybe not this size, but actually, huge VRAM, GDDR5, for example. Okay? The thing is that this memory is very limited, this one, but the access is super fast. Super fast, but this is like some kilobytes maximum. So this memory and register memory and so on is used for the immediate variables, and you have a limited amount of them. So per shader core you have typically on modern hardware like, I don't know, 96 registers or something. So let's say you can keep 96 floats in the immediate memory. But if you want to read something so huge as a texture, then it won't fit here. You have to go all the way to RAM. Let's say there is some texture it doesn't look like that, of course. I'm just, you know, making this up, but in general, there is some texture and you want to sample this place, for example. You're interested in these UVs. This is a whole texture and you want this. Okay? So it gets you this sample. It goes back all the way, actually, to the cache. And for a moment, for some short time, it will keep this in the cache, this pixel and its immediate neighbors. Because if you sample this place with your current UVs, there is huge chance that the next pixel will have similar UVs. So it's worth it to take more than you just requested, just in case that the next shader core actually wants, hey, I want the same thing, just this pixel, the neighbor. Cool. So small part of the texture can be held in cache, but it will only make the next operations faster. In the meantime, this thing can take like 200 cycles or so. Even if it were less, even if it were 100, this is still huge. This is like, you know, doing sine 5 times. This is long, and this probably it will get even longer depending on, you know, the texture content and so on. So the journey to VRAM and back takes a long time, okay? You want to avoid that. But the compilers are clever because they are computers and they know magic. So let me show you what they will do. If we have such example, they can do nothing because the sample goes at the end. But what if we had some calculations independent of this texture? If we had, for example, I don't know, some param that would be, I don't know, layer height. Okay, height of player from the ground, and we want to apply, let's say, sine on that. We want to, I don't know, take also a cosine of that. We want to check which one is bigger than the other, and later we want to, I don't know, take UVs. I'm making things up completely, just, you know, to make some heavy math. Take UVs and multiply that. You may think this is a lot of operations, or I don't know, even worse. Take tangents of the UVs. Then, okay, and multiply that. And put it, add it, let's say, to the texture result. Like so. Like so. This is completely stupid, but it doesn't matter. So we have texture, which takes a lot of cycles to be delivered from the VRAM. We have heavy calculations. Let's comment this by naming it heavy calculations. Okay. And this will be heavy texture sampling. So you might think that this heavy thing plus this heavy thing will make a twice as heavy shader. It's not true. I will show you why in a moment. Samrat asks if having 12 texture samples in a material is not a very good idea. It's not. You're right. It's absolutely not. But there's one trick now. Having fewer texture samples, but a lot of math, can result in some free math. Math for free. How is it possible? Take a look. We are waiting for a texture. Okay. It will take hundreds of cycles to go back to us. So the GPU is idling, it's waiting. So why not calculate the texture independent stuff in the meantime. Okay? This shadows this math, because it will take so long that we have cycles for free while we are waiting. So we can calculate all this and don't even see a difference. This compared to this will probably take exactly the same amount of time, or very similar. Now take a look at the assembly. Float, texture sample will be texture. We need to make a texture. So uniform texture to D, my text, and there will be also a uniform. Uniform is a parameter in HLSL. Yeah, the result should be texture sampled like this. Now about these UVs, let's make our own UVs, like we have in Unreal. Our UVs are multiplied by tiling, okay? Tiling. And now, let's remove that. And now there will be float UV equal to input UV times tiling, okay? Times tiling. And here. Let's see. Okay. So what we have? We have a multiplication here. By the way, buffer load is loading a parameter or something else, some other constant. That's the same for entire shader. That's why it says it's scalar memory. So things that are the same for the entire material, but still need to be calculated, are scalar memory. Things that are dynamic per pixel or per vertex are vector memory. The name doesn't, you know, scalar or vector, it doesn't have anything to do with float or float4. It's just the name for the type of memory. Scalar is operations for the entire shader, vector per specific pixel. So yeah, we wait for these parameters to be retrieved from the memory. Then the tiling, where it's already, let's say, downloaded from the memory, it's multiplied with the UV here and assigned to a register. Then there is image sample, so reading a texture under a given UVs here. My text sample is the same as in Unreal texture sample, okay? And then the result is put, like mov, it's assigned to the output and exported. This is it. So now, what would happen? In theory, what you would expect to happen is, if you do some math after this texture, it will be applied later. But as I said, it doesn't work like that. It's much more clever. We will add something called heavy calculations input. Cool. And there will be a function float heavy calculations that takes PS input and returns some heavy result. In our case, it was player height, sine, cosine, max, tangents of UV. Heavy calculations, max, cos, uniform. Thanks, Samrat. Okay, fantastic. There is a wait counter here, but it probably waits for this uniforms. And wait counter basically says that at this point you have to stop because the next instructions depend on what was being loaded. So you can do whatever you want here, but here you have to stop because you will need that later. So now there is, where is it? Yeah, before image sample, there has to be a multiplication because image sample depends on the multiplied UVs. So we have to interpolate, so get UVs from the vertex to pixel, interpolate UVs here, this one, then we have to multiply by tiling, and only then we can sample the image. But it doesn't immediately sample, it just sends an instruction to sample and then continues with the flow. So while this is going all the way to the VRAM memory, is doing next things. It multiplies, applies cosine here, applies sine here. It does that 2 times, probably, because of the tangents. Then it takes the maximum of these things, this cosine and sine. Then it multiplies here by the tangents result. And only then, after all this is made, all these calculations, here it has the weight counter. So only here it resolves the, it really waits for the result of the texture. So even if the heavy calculations appear to be done after the sampling, they actually happened during the sampling. And only then there is a weight counter and addition here, and it's put to the result. Move, export. Okay? So this is it. Basically, sampling a texture can shadow a lot of calculations, making them basically free, often, depending on how heavy the texture is and how lucky you are with the cache. As you can see, if the neighboring pixels were already sampled, then you may get this also cheaply, but if your UVs are chaotic, then you paid heavy cost. Which is another thing, by the way, that look at this. If your UVs are kinda consistent, let's say, I don't know, you have an object, right? And then you have your X of UVs going here, you have your Y going here, and basically if this is a nice smooth gradient, like a typical UV, then it's good, because one pixel samples this place, another pixel here, another here. This is all coherent, okay, in terms of standard UVs. But if you apply some weird effect to your UVs, let me show you, then this would be much more expensive. What I mean is that this is how standard UVs look like. Frac. Oh, why is it so slow? Come on. Real time. Can I disable real time? I should be able to, yeah. It became nearly unresponsive. Okay, standard UVs, how do they look like? Come on, Unreal. They look like this, right? That there is unlit, yeah. X is going one way, Y is going the other, and the yellow is basically 1, 1. Here, 0, 0, 1, 1. Now, these are nice UVs because the neighboring pixels sample from a very similar place. So the texture can be placed in a cache. So when asking for one value under some UVs, the pixel already gets the neighbors and puts them in cache to avoid unnecessary waiting for the neighbors. However, if you have a noise, for example, vector noise, you take a component mask R and G and you add this to the UVs, like so. Because we need some fancy effect, okay? If you do that, and the UVs look like this, maybe not as noisy, can be weaker, Yeah, let's say if you add some noise to your UVs, okay? This may be a really nice effect, but what it actually will do is that you can no longer rely on the neighborhood, because if one pixel samples here, but another, due to the noise, samples here, another here, and so on, then the cache doesn't apply. It doesn't apply. Because this one will take these neighbors. This one will try to use the cache, but this is out of the cache, so I'll need to sample again. So noisy UVs or incoherent or many splits of UVs will make you pay a higher cost when sampling. Okay? So Legomi asks if it's better to do glitches on texture rather than on UVs. Often I'd say yes, though it depends, because sometimes a glitch on the texture will require another texture to sample. So sometimes it's okay to add some subtle UV glitches. Or sometimes you even have to pay the cost, because if your effect is dependent on it, then there's nothing you can do, right? But in general, yeah. If you can avoid very noisy, incoherent UVs, then do that. Also, there's another thing. Textures have mipmaps. That's because, let's say this is an object of this size on the screen. But if you are far away, here, then your UVs are different, because your UVs suddenly will be like, I'm sampling this part of the, let's say if this is a texture, okay? If this is a texture, text. Then if you have neighboring pixels on the screen, usually GPUs work in groups like 16 by 16 pixels or something, 8 by 8. So if this is my group here, this is a whole different story than my pixels group of the same size here. You know, this object is further away, so suddenly, while this was doing a nice use of the cache, because this was sampling here, 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 and here, for example, then immediately this far away object here, this one, it will sample like here, 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 and here. So completely, you know, it doesn't work for the cache. So this is why mipmaps were invented. This is why blurry textures are good. Mipmaps are versions of the same texture but smaller, right? You probably know that. So smaller, 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 smaller until 4 pixels by 4. In that case, it knows that the UVs change so quickly that it doesn't have to use this. It can use that with the same result, because this is a resolution enough for this size on the screen. So this object will use MIP 0, while this object will use MIP 2. Okay? So this is what mipmaps are for. And if you disable mipmaps because of blurriness, don't do that. Don't do that. This is very, very good for the cache. This may be one of the reasons that modern games can apply so many textures. Because you have, normally you'd have like billions of samples to take per frame, like impossible. But thanks to cache and mipmaps, usually this can be avoided. In reality, we pay like 1/10 of the cost or even less, okay? Because if UVs are coherent and mipmaps are there, then usually you sample from a very small texture in practice and you utilize the cache in shader cores. Okay, do you have some questions so far? And by the way, about resources, this is a hard read, but very much recommended. Fabian Giesen, he has a series called Graphics Pipeline, a trip through graphics pipeline. Basically, it's a trip through, let's say, modern, by that time it's 10 years old, but still quite modern, graphics pipeline. So if you stumble across some old OpenGL ancient resource, then this is a very good refresher of how things work, let's say, now. Because nothing has, not so many things have changed actually. Ray tracing is a new thing, but it doesn't change this thing. Rasterization is very mature at this point. So very much recommended. Trip through GPU pipeline. Legomil asks, what if you have few samplers to one texture? So what if I put this texture on the left, this texture on the right, and then sample few samplers but the same texture? The thing is, it doesn't save much. It doesn't save much because what's costly is sampling. So texture, okay. Atlasing textures in a bigger atlas, sometimes okay, because you save on the number of files, so streaming. But you still pay the cost of sampling, which is the worst in the shader itself. So combining textures only helps outside of the shader, but in the shader itself it doesn't save much. But you can do another thing, which is actually very useful. You can aim to reduce the number of samples. Okay, so if you combined, let's say, this is a color example, so it has to stay like that. But what if you actually what if you actually did only one sample? So in that regard, there is a plaster and there is some shape. If you are okay with the fact that the shape will be one color or grayscale, you can pack them into RGB. Do I have designer here? I do. Okay, there's substance designer. Come on. New substance, yeah. Now, let's say we have some black and white spots. And let's say we have some crystal. Cool. Now, if I'm okay that I will use these two with the same UVs, and I'm okay that they're grayscale, then what I can do is to merge RGBA. I'm packing this into red and packing this into green. Into blue I can pack even some other noise like this with different scale. And the result is this. In the red channel, it has my first texture. In the green channel, it has my second texture. And in blue, it has the third one. So let me export this thing and sample it in Unreal. So let's save that. Let's save that as bitmap. Test material. Let's jump to this one. Okay. Compression will be masks. Cool. And you can see red, green, and blue. Okay. I save that. And now I can get rid of this because I will only sample once. And this will be these masks, texture sampler type masks. Cool. And yeah, come on dogs. And now I can make a gradient. Sorry. Content drawer. Let's make a gradient asset. I should have imported this here. What? What's that? There is some gradient asset, right? There was something. Materials. How was that called, guys? This curve atlas thing. Curve linear color. Okay. Was that it? Yes. Awesome. Okay. Can I select this as a color? Or I have to use these weird things? Ah, yeah. Choose color. Through, let's say, yellowish, sand color to white. Alright. Choose color darker. Nice little gradient. Very cool. Now this is one curve. Now I need another curve. Now in the atlas, I add another curve. They are here. And the hive automatic. Jeffrey asks if I'm going to use that to colorize grayscale images. Yes, absolutely. Let me prototype that in, but this is what I'm going to do. If I have this on the output, I could do a gradient map like this. If my gradient contains colors, like so, then you can see that it's colorized based on this gradient. So grayscale is used to pick the value from 0 to 1 on the gradient and apply it as a color. This is what I'm going to do to use grayscale masks as a base color, because I will use grayscale masks plus gradient. So the same in Unreal. I have my grayscale masks here. These packed here, and I will use gradient mapping. Where is it? Okay. So curve time from 0 to 1 will be my red from this. Let me preview. As you can see, what we have in Designer, that the gradient, this one, colorizes this. Okay? I need to modify it a little, like so. Now it's better, yeah. Super retro look, by the way. So this is one gradient, and there will be gradient 1, for another one, for the green one. If I use the same grayscale, hey, wait a second. It has to be square, or? It seems like it has to be square. That's weird. Okay. Anyway, yeah, so based on which gradient I'm using, I'm getting a different color, right? So now this I will use for red, this I will use for green, which is another pattern. And now I can lerp between the results having just one sample. So one texture, one sample, instead of two textures, two samples. And as you can see, stop previewing. Yay! I have my mixed result. Just like this. So, see you.